Okay, hello everyone. Welcome to today's IAS Distinguished Lecture. So it's my pleasure to introduce our distinguished speaker today is Professor Jürgen POPP. So Professor Jürgen POPP has remarkable academic journey. It began with the Julius Maximilian University of Würzburg and then the University of Erlangen-Nuremberg, followed by a postdoc research at Yale University. Oh, he's my alumni. So after completing his habilitation at Würzburg University in 2002, he joined Friedrich Schiller University, Jena, where he holds the chair of physical chemistry. He also served as the scientific director of the Leibniz Institute of Photonic Technology. So Professor POPP is a pioneering figure in biophotonics, where he develops innovative optical and photonics technologies with some groundbreaking work combining multi-scale spectroscopy and multimodal imaging with particle and chip-based molecular diagnostics, enhancing crucial areas of medical including pathology, oncology, and infections diagnostics. And he's also served as the founding editor-in-chief of the Journal of Biophotonics and also the Translational Biophotonics. And he will continue to shape the directions of this dynamic field. And with his outstanding work, he has been recognized through numerous prestigious honors, including the Pittsburgh Spectroscopy Award in 2016 and the award for the Berthold Labinger Innovations in 2018, and also the Ralph Daffendorf Prize for the European Research Area in 2019, and the Charles Mann Award for the Applied Raman Spectroscopy of the Federal of Analytical Chemistry and Spectroscopy Society in 2023. He's a fellow of several esteemed societies, including the Society for Applied Spectroscopy, the International Society for Optical Engineering, the Royal Society of Chemistry, and most importantly, is the German National Academy of Science and Engineering. Okay, it's a long introduction. Now, please join me to welcome Professor POPP. So he will start sharing his insights into the very cutting-edge developments for AI and biophotonics.
Yeah, many thanks for this, first of all, kind introduction, for the invitation to be here at the university. And yeah, it's my pleasure to talk about our findings, where we try to combine biophotonics with AI. And we believe that this will be the solution, a good synergy in order to improve personalized diagnostics, but not just the diagnostic, but also pave the way into new ways of therapy. But before I'd like to start, I'd like to give you a little bit of insight where I'm from, coming from Europe, coming from Germany. You can see in the center here, you can see Germany, and here I have a glance where Jena is the city of light. So we are in the center, it's called Thuringia. Now you can see Jena. It's a small city having something like 105,000 residents. And I think it's very popular when you have been dealing with optics, photonics, then you should know Jena, because there are three very important people called Carl Zeiss, Ernst Abbe, and Otto Schott. I'm showing this not to go into the history, but I'd like to show you what I would say modern research is somehow about. Here you see Carl Zeiss, and he started his company, the Zeiss company, as a manufacturer of, let's say, microscopes, but more or less by trial and error. What do I mean by trial and error? More or less taking pieces of glasses, lenses, putting them together and try to build a microscope. But this was not building on design or understanding, it was just by trial and error. It's even called Pröbeln. Then he got in contact with the mathematician, the physicist, Ernst Abbe, and now they can really design a microscope. Abbe came up with this famous upper limit of diffraction, so what can be resolved by using optical light. But still, both were not able to build microscopes, good microscope. Why? What is the missing part? It's glass. But you need optical glass, you need high quality glass. So just when they couldn't convince Otto Schott not to build the company, the glass company in Wiesbaden, but in Jena, then this was the starting point of two big major companies. One is Schott, one is Carl Zeiss. But still, there's something missing. And this is also what is driving nowadays the field. Certainly you need the interaction with the biologist or the medical people. And here you see two examples, Matthias Schleiden and Ernst Haeckel, both of them very famous biologists, and they were quite important in order to foster the field towards, let's say, what we nowadays call biophotonics. So this was the past. What is Jena nowadays? Certainly we have the university, we have the University of Applied Science, we have the hospital, and what is very important also for the hospital, they have three major research topics. One is on cancer, one is on infection, and the third one is on optics and photonics. Even a medical hospital is working in this field. And then we have also the so-called Beutenberg campus. I will come back to this in a second. Then what is also quite important, we have a really living industrial infrastructure, and something like 20,000 people. You have to keep in mind, it's a small city of 100,000 people, 20,000 people working just in the field of optics and photonics. And this already means that there is a lot of things going on. And if someone is dealing with optics and photonics, this is a great environment because you have also a lot of companies working in this field. And I will come back to this during my talk. Well, let's come to the Beutenberg campus. This is something very special because before reunification, this was more or less an empty plane. After reunification, this has been built. So here you can see now a nice collaboration of 9 research institutes. We have 2 technology centers, 50 startup companies there, more than 3,500 people work in this Beutenberg campus. And what is also quite nice, we have here different institutions working together. So what you can see here are, for example, the Leibniz Institute. So we have here 2 Leibniz Institutes working in the field of life science. We are the 3rd Leibniz Institute, and if you know the German research infrastructure, so we have Max Planck, we have Fraunhofer, we have Helmholtz and Leibniz. Those 4 are funded by the federal government. And for example, the Leibniz Association has something like 95, 96 institutes, something like 10,000 scientists working, and the budget is something like 3 billion euros. We have 3 institutes here on the Beutenberg campus. Then we have Fraunhofer. You can see we have here Max Planck. We have the university, but we have the spin-off companies. And this is a nice environment, really, in order to get things done, but not separately, but in collaboration. Well, if you come a little bit closer, then you can see here the Leibniz Institute of Photonic Technology. So this is our main building. Then we have a clean room, a laser facility, and here back you can also see we have a fiber drawing facility. So let me just introduce briefly the research profile of the institute. So we are doing research related to the unmet need coming from the medical field, the field of health, security, environment, and energy, and what we like to provide with 3 program areas. 2 of them are very applied, fiber optics and photonic detection, and 2 are very technology driven, and 1 is very much applied. This is the field of biophotonics, and what we like to provide are photonic solutions for the field of life sciences, and therefore we can easily describe the institute with the slogan Photonics for Life. But what is also quite important to know that it's not just about high impact publication. So excellent research is one of the most important topics, but very often we want also to go for the instrumentation. So the other slogan in order to describe our institute is from ideas to instruments. So you will also listen or see in my talk what is meant by we want to go for the instrumentation. Yeah. Well, what is the mission? It's quite simple to describe. So what we want to provide are photonic solution for a faster and more accurate medical diagnostics. So this will be the major topic of what I will talking about, for safe medicine, for new quality of food and environmental analysis, as well as for alternative energy sources and innovative security technologies. And what is the vision behind this? We want to make our life safer and healthier. Just let me give you a brief overview about something which is for us quite important. And this is also why it's important to be part of the Leibniz Association, because here we can provide, for example, infrastructure for our researchers. And one of the most important infrastructure is fiber technology. So even when you think about medical research, if you think about producing your endoscopes, so what is then quite important? You need to have hands-on on the fibers. And so we can start with the class, the preform. We can go for structured fibers. And here you can see what type of fibers we do. The diameter is something like 100 to 120 microns. So we start here with something 1 or 2 centimeters. We make the preforms. We can draw our fibers. So these are quartz fibers. So this is here, the temperature is around 2000 degrees Celsius. And out of this, we can make this fundamental new type of fibers. And certainly this fiber needs to be characterized. They can be also post-processed and functionalized afterwards. And what we are very much interested to use them either as a light source for specific wavelength range, for example, for the IR, the NIR range, this is quite important for us, or just to use it as a probe inside the body, for example. Well, then we have a clean room. A class 4 clean room. This means 4 particles per cubic meter are allowed. And here we have all the different technologies in order to produce, for example, here microfluidic devices, or we go for single photon counting detectors, or we can go for some meter materials. And here some further examples. Oh, sorry, this is the wrong one. So here some further examples are shown. We can go for IR sensors and also for thermal sensors, microfluidic devices, some chip sensors, but also we are working in the field of quantum technology, producing here, for example, qubits. Here you can see 4 qubits. Now we can go up to 20 qubits, which is quite important for example, quantum technological annealing. Well, the third key enabling technology is about photonic data science. Nowadays, we will call this AI. But it's not just using AI in order to solve something. Photonic data science is even more, because if you want to use AI in order to interpret your data, so what is also quite important, you have to design your experiment in the appropriate way. Especially if you want to go in the medical field, you have to think about what is your control, what is your healthy cohort compared to the disease cohort. How many people I have to include? And then you have to come up with the experimental design. For example, if we could talk about cancer imaging, then we produce a lot of images. Then you have to think about how can I interpret this data? And then at the very end, I will come up with some models and some interpretation. But this is also valid for spectral data, because this is also something we are producing en masse. And therefore also here we have to start with the task. So this is not just about AI, but this is about photonic data science. This is about the life cycle of data. And at the very end, it's also quite important how to handle and store the data in order to reuse them according to the FAIR principle. Yeah. And the last topic is system technology. And here you can see when I was talking about going from ideas to instruments. Instruments means really that we are able to produce some devices. For example, here, this is a so-called invascope, which has been used or is being used inside humans, for example, for bladder cancer diagnostics or for head and neck cancer diagnostics. And this is a device developed according to the medical device regulation. Then here we have something very nice. This is just a rendering, but this is a microscope. And here you can see the microscope objective. This is an optical fiber, which is being introduced deep into the brain. And this is what I like very much, because here you can check. This is the group of Thomas Gismer, and he's doing excellent fundamental research. So he's publishing a lot of publication in Nature Communication, Nature Photonics. But even he's also now pushing this technology towards a spin-off company, which is called Deepen. And this is what I meant before, going from ideas to instruments. So when it's needed, really go for the instrumentation. And here have a spin-off company, and they try to commercialize this type of microscope. What you can see here, this is something I will come back later during my talk as well as. So these are also two technologies which have been already implemented inside the hospital, being developed from scratch, but now being used in the hospital in order to go to the medical applications. Well, just to summarize, what is the Institute about? So we are something like 420 employees. This was 223. Now we have something like 450 employees. We have 120 PhD students. As you can see, we are very international. They are coming from 35 countries. Our researchers are from, are international with something like 51%. If you just look to the PhD students, they are even from 75% are coming from abroad. And here the publication, but also you can see we are filing a lot of patents in order to protect our IP. Just a quick introduction into the Institute. Now I will start with my presentation about biophotonics and AI for a synergy for personalized diagnostic and therapy. I'd like to talk about two topics related to the major megatrends. One is with the aging society, and this is about cancer diagnostics. And the other topic is related to the megatrend of the mobile society. This is about infection diseases. And let me start with the infection diseases. And I think this is a common scene. You are going to the physician, and at least in Europe, but also in the US, very often you end up with, let's say, a prescription. And this interaction just takes something 20 minutes. There was no sample being taken. And very often you end up, for example, with an antibiotic treatment. And now the question is, why do I get an antibiotic? Maybe this is just related to a viral infection. An antibiotic won't help. And even more, if it's a bacterial infection, you may be resistant, or your bacteria may be resistant against this antibiotic. And therefore, our aim is we want to develop techniques which allows us a precise diagnosis before a target, really important, a target therapy can start. And when we talk about infection, then you can easily go for two ways in order to interpret the infection. Well, the first way is you can look at the immune response, because if you are infected, or if you have, for example, also cancer, if you have an allergy, your immune system is always reacting. So this is something we are very much interested in. Can we learn something by using optical methods, going for example, blood sample? Can we learn something about your immune status, and does it tell us something about what happened to you? The other way is, if you know that this is an infection, certainly then you can look what type of infection pathogen you have. And this means you isolate the pathogen, and then you have to identify the pathogen. And if these are bacteria or fungi, then you have to look for the resistance. Well, why is this immune response quite important? Because, or not just more important, but because it's also easy accessible, because you have just to withdraw a little bit of blood, and blood isn't having the white blood cells, and this gives a lot of information about what has been happening to your body. And for example, if you look at the leukocytes, then they are responsible for the sensing of infection, but also they are sensing the tissue damage. And what you can easily see there is the basal state, if nothing is going on. And if something like an inflammation is coming or an infection is coming, then you are going to the activin states. And this is changing the chemistry, and this must be somehow visible. So you need to test this. And if you have a blood culture, then you can easily go also for antibiotic sensitivity testing if you have, for example, a bacterial infection. So these are the different aims. And what we are doing here very often is we're using Raman spectroscopy. Why? Because Raman is one of the most simple technique you can use. So, for example, we built a Raman microscope in such a way that we use something like a laser pointer. Then the laser pointer is put on the sample. Now what you see from my hand is more or less the elastic light scattering from my hand. And if you look very precisely, you will see there's something which is not almost visible. But if you remove the green light, the elastic light scattering, then you will get the inelastic light scattering. And this gives you information about the molecules being present. And you can build a Raman device nowadays, very small, very tiny, very cheap. And this is what we are trying to use. And as you can see, pointing the laser on, for example, a bacterial cell, you get what we call a molecular fingerprint information. But since we are not dealing with abiotic particles, but with biological particles, and most biological cells are quite similar, certainly you need some, let's say, what we call photonic data science in order to interpret the data. Nowadays, people say AI. I'm saying we can go from simple chemometrics to machine learning, or even for the deep learning. Yeah, so it's depending on what is the task, how complicated it is, and how many data you have at the very end. Well, what does it mean for Raman? We want to translate what we find in Raman. For example, if we have the basal state and we have the activated state, then certainly we need to find what is the difference, what are the small molecular differences. And very often it's just one, let's say, change in the surface. There is one receptor popping up, and therefore you need somehow this machine learning in order to translate this Raman score into something which is related to the response signature of a disease. Well, this we published, since we are working on this for more or less than 15 years on using machine learning. So we have published this in Nature Protocol, but this is not just about this machine learning, but it starts already, how do I define my task in a proper way? Then how should the experimental design looks like, so that you don't produce a bias just because of your experiment, or you produce a certain result because of your experiment, not because of your sample, but the way you perform your experiment. Then you need the data pre-processing, the data learning, model transfer, model analysis, and this has been already nicely described. And then certainly you have to do the validation, and internal but also external validation. And we have even developed the software which is called the Raman Metrics, and which is available also for other scientists. So this is something which is quite important for us. And now I'd like to show you a little bit what was the way going towards the medical diagnostics in order to use, for example, Raman as a point of use Raman spectroscopy. So this is in 2003, my lab when I started, and you can see this is what the typical laser looks like. These were argon ion lasers, so we have 2 or 3 lasers in this way. Even a UV laser we have back here is the microscope, and then we have big spectrometers. And this was in 2005, the first, let's say, miniaturized way, but still quite bulky. I would say this is portable. Then this is a device which is still quite large, but this is working completely in an autonomous way, so that you don't have to have an interference with the user, or what the user has to do. He has to put, or she has to put the sample beyond the microscope, shut the door, and then everything is done in a complete automatic way. And as I said, this is now being introduced in the hospital. This is in the clinical microbiology lab at the hospital of Jena, and here we do a lot of work research on the host response. And this is our latest version. You can see here it's very miniaturized, and you see even a lot of space, so there's even further let's say space for improvement of a miniaturization. And our goal is at the very end to have a Raman microscope which can be used for life science applications. So you can have small microscopes already, but these are not applicable for the life science application. So this is the idea, to have them really very small, and I will show you why we need to have this small, because we want to have this in the doctor's office. Well, now let's come to the immune response. What can we do and learn about white blood cells? So white blood cells, the leukocytes. This is the most common test in a hospital. And it gives you good information about your immune disorder, about infection or inflammation. And it's easy, accessible, and just 1 milliliter of blood has a million of leukocytes. This means you have a lot of samples. And we want to prove, can Raman spectroscopy, first of all, differentiate the different immune cells, and can we learn something about the immune cells? Why is this important? And here you can see the overview on these different white blood cells. And what is quite important, as I mentioned already, when they are interfering, for example, with different pathogens, then there is a different response. You can nicely see that there are changes. I'm not going into the details, but due to the cellular response, there's a change in the chemical composition, the molecular composition. And this is why we'd like to use Raman spectroscopy, because Raman gives you direct this information. And now the first question was, can we really identify the different white blood cells by using Raman spectroscopy? And in order to do so, what we did is we scanned over the single cell and many of the single cells, and then we get this Raman data, so the neutrophils of the T lymphocytes, and you can easily plot those data in a false color plot where you can see, oh, this is a monocyte, this is a lymphocyte, this is a neutrophil, when you plot, for example, the DNA versus the cytoplasm. Now the question is, in order to really get something about the immune status, it's not sufficient to identify a single cell. This is, let's say, a monocyte, or this is, for example, a neutrophil. So the question was, how many cells do we need to measure to get a really good statistical value about the distribution of these different white blood cells? And here you can see the predicted fraction. If we measure something like 100 sample per patient, 100 cells or 500 cells, what you can see here, if we just measure 100 cells, then you have a quite large distribution. If we go for something like 5,000 cells, then the distribution is converting to a single value, more or less. And this means your prediction of this value is quite, let's say, solid. And therefore, we decided we go to between 1,200 to 1,500 cells we measure per patient, and this should be then sufficient to the health studies. And then we did our first hemogram of blood. We have done this white blood differential count being done. This is for healthy donors, but also for patients. And you see the Raman readout in green, the clinical readout, and you can see the numbers are quite well. And this is everything well within the total allowable error. This already shows that Raman spectroscopy can do this, but to measure something like 1,000 cells from a patient, then you need to have a different device. Because measuring point by point, and if you think about each point takes 5 seconds, and you measure something like 100 points per cell, this will take forever. So how can we improve this? Now, coming back to this device, this is very particular in terms of we use light scanning, we use a rapid mean spectral acquisition, and mean spectral acquisition means we have just one spectra taken per cell. So this we open up the focal plane. So this means we have a focus which is 8 micron in diameter. So we can take one spectrum, we get an average spectrum. And what is also quite important, we have completely automized everything, and we are going for low resolution Raman spectroscopy. What does it mean, low resolution? So normally spectroscopists are very much interested in high spectral resolution. You want to go for 1 inverse centimeter at least. If you look at the biological features, then you can easily see, oh, they are quite broad, at least 10 to 20 inverse centimeters. So there is no need to be better than 10 to 20 inverse centimeters. And therefore, we open the slit, and therefore more light is getting into the device, and this way we can easily improve the measurement time. And you can see here, normally we take something like 0.2 second per cell, and here we measured something like 24,000 cells in 1.3 hours. And if you think about 1,200 cells being measured, then this is being done in a very fast manner. And here you can see everything which has a red cross inside, this is being measured, and this in a complete automatic way. Now let me show you what the synthesis or the isolation process is about. So we take blood, we do some centrifugation, we do some lysing, and then that's it. It takes something like 10 to 12 minutes. Then we do our measurement, and within 60 minutes we get all the information in a complete automatic way. You can see here the measurement, you see the cells, here you can see which cell have been measured, here you see the Raman data. And we have an autofocus device so that we always in focus on the cell. And what you can see here in this plot is that these are individual patient. Each dot is one patient, measured something like 1,500, 1,200 cells. And here we have viral infection, the green one where some bacterial infection. Just to show this in the overview. So what is needed is a drop of blood. At the very end, we use just 500 microliter of blood. We have this high throughput analysis. Then we do here some LDA analysis, PCA combined with an LDA. Then we can nicely identify this is a viral infection, this is a bacterial infection. And coming back to my first statement, what we want to achieve is we want to have an objective information which allows the physician really to go for a target therapy. And this is one is already quite nice because here if we know this is a viral infection, we need an antiviral treatment. If this is a bacterial infection, we need an antibiotic treatment. So this means with the spectroscopic information, we enable the physician for a diagnosis-driven therapy. So this is one step. And what you have to keep in mind, this entire process is not longer than 60 minutes from taking the samples to get the result. Well, then we were also very much interested, can we even learn more about those interactions? That here we look, for example, at the neutrophils and with SARS-CoV-2. And what is quite important, if the neutrophils are not activated, they don't interact with SARS-CoV-2. So activation is of utmost importance. So this has been done by our immune system, but we can easily also prove this in vitro. So what you see here is when we look at non-activated neutrophils. So here you can see the MOC is the control. And here you can see the white blood cells, the neutrophils with SARS-CoV-2 after 3 hours, after 24 hours. This is the PLS prediction. You can see there is no change. The prediction accuracy is around always 40 to 50%. So this means there is no change going on. If we do some activation, for example, with TNF and with LPS, and this after 3 hours, you can see there's already a prediction accuracy going to 60 to 80%. And if you go from 3 hours to 24 hours, you can nicely see that we have a prediction accuracy around 70 to 85% between the MOC, the control, and the infected cells. And here you can nicely see how important the activation is. But this is not what we were so much interested in. We were interested in, can we see this difference between the neutrophils being in contact with SARS-CoV-2 or not? Well, and then another question was, there we used some cell lines, so-called Vero E6 cell line, and we were very much interested, if we take two virus particles, which are different, but somehow from the size and the shape and the chemical composition are the same. And for example, here SARS-CoV-2 and the measles are quite similar in size, but also the chemical composition. The question was, can we separate this? Just by using Raman spectroscopy. Keep in mind, Raman spectroscopy, as I said, the processes are always the same. And what you can see here is in black. So this is the Raman model for the measles. And here we have in gray the control, and in blue the measles spectra. And you can see we can nicely separate them just by using Raman spectroscopy. On the single cell level, here we have now SARS-CoV-2 and the healthy control, and we also can nicely separate the cells, meaning we can separate a measles infection from a SARS-CoV-2 infection. And this is what we are aiming for. Can we use more or less the white blood cells at the very end in order to also identify, just from their signature, what type of infection has been taking place? Is it a flu infection? Is it a measles infection? Is it a viral infection caused by SARS-CoV-2? And it would be even nice if we can go for the different variants of SARS-CoV-2 infection. But certainly working with SARS-CoV-2 is a little bit more challenging because you need an S3 environment. This luckily we have in Jena, but still it's a lot of work to be done, and the experiments are quite tedious. Now come to the characterization of the infection-causing pathogen itself. So what our aim is, we isolate the bacteria, for example, out of urine or out of blood. And then we have developed the so-called Raman bioassay. This is a chip-based approach, where we are able, for example, by using electrodes, and here we put alternating currency on this, and we have here plus and here minus, and this is changing with something like 10 kilohertz. And then we can easily push our bacteria into the center. This has the big advantage. We know where the bacteria are. And this means we can focus our laser here directly into the center. And what can we do? We can take something like a molecular print information on the bacteria itself without any antibiotic. But since we are using a chip system, we can have one of these containers filled or not filled with antibiotic, and the other containers, for example, we have filled with different antibiotics or one antibiotic with different concentration. So this means that we can look in a quantitative way on the interaction of the bacteria with the antibiotic, as well as the control allows us to identify what type of bacteria we are dealing with. Well, here you can see we are looking not just at the Raman data itself, we are looking also at the morphological change, because both can occur, a change in the Raman data as well as a change in the morphology, and both information can be used directly. Then we want to determine the antibiotic sensibility with help, as I said, the morphology and the quality of the spectral change. And here you can see, for example, E. coli interacting with ciprofloxacin. So these are the different spectra, and here we did some concentration profiles. And here, for example, in the range where we have the CC stretching and the DNA band, we have a nice change in this band. And this can be used in order to quantify not just that there is a sensitivity present, but also to go for a quantitative way to interpret this data. And certainly this we have done also for many other, for example, here germs, isolates coming from patients. What you can see here, this is the classical microbiological readout. The numbers here, this is the minimal inhibition concentration. So this is the classical standard, whereas it needs at least 24 to 48 hours. This readout we get latest after 3 hours, and you can see we have a perfect agreement between what is the standard to what we can provide by Raman spectroscopy, and in a much shorter period of time, which is essential at the very end in order to being used for the patient being in a critical care. Well, and as I said, we are working here on a device which is being miniaturized further and further, and this is the chip device. We are also working in terms of optimization. So, for example, all the chips can be measured in a complete automatic way. They can, by a robotic system, they can be loaded into the device, and also the handling of the device. For example, here, this is a different chip holder, is also done by a robotic system. So this is something which is being used now in the hospital, in the clinical hospital of Jena, which allows us to work in an open system, because here we have an S2 environment, so we can easily do this. But the next generation will be something where we use a cartridge which is completely closed, and this we will introduce then to the doctor's office. Well, and here you can see what we want to achieve. Just to summarize here, so this is a normal way. For example, if you have a blood infection, then there's a blood culture being taken, then there's the growing of the isolate. The isolate is being then introduced on the Biophotonics, and then afterwards the antibiotic sensitivity testing is being done, and this takes up to 3 to 5 days. So this means many people die before, especially in the intensive care unit. And our approach is that we want to go into this window that we are just using 3.5 hours after a positive blood culture. And that this is somehow working also with different patient samples. So these are now real patient samples. And here you can see the clinical readout. And here you see something like, first it's growing, and then you can see we have a MIC, which is around 0.6 milligram per milliliter, because here you can see that the optical density is going down, but the readout is after 18 hours. And here we have the Raman readout. Keep in mind, this is 90 minutes, and you can see that we have here, this is our control. This is, so to say, our zero line, and then we do this different spectra. So this is a sub-inhibitory concentration. As you can see, it's still growing, but here we have the inhibitory concentration, and you can also now nicely see using here some PLS as well as then the treatment concentration, that we can nicely see the interaction. And this is working also for certainly with other bacteria. So this is E. coli and ciprofloxacin. This is with Staph aureus and oxancillin. The same behavior, but here we have directly positive feedback. And here again, 18 hours, 90 minutes, the Raman readout, it's perfect matching, but we are much faster than the clinical technology. And so what is going on? Certainly, first of all, we want to use these devices now in different clinics. So we will go for more like a small series production. And certainly we have to work on the handling of the calibration effort, because even if you are using deep learning, the problem is if you have one set of data being produced with one Raman device and you want to go with to another Raman device, you need really to transfer either the data or the classification model. And this is quite challenging, so we are still working on this. And certainly we are also like to simplify the test and the chip device. And certainly we want also to develop the AI further, because also there we see room for improvement. Let me come to the second topic. It's about cancer diagnostics. And I'd like to show you more or less what is the situation now in the hospital. Well, if someone has been diagnosed with cancer, in order to localize, to identify where the cancer is, there's a lot of techniques around. You can use ultrasound, computed tomography, MRI for the identification. When it comes to the surgery, it's more or less like almost 20, 30, 40 years ago. Because very often they are just using a magnification lens, an optical microscope, a surgery microscope, or an endoscope. But there is not too many different, let's say, optical techniques around which give you really a sophisticated insight where is the tumor, where the tumor margin, and where it is, for example, inflamed tissue or, let's say, dysplasia. What they do is certainly they cut out what they mean is a tumor, then this is sent to the histology lab, and this certainly takes a lot of time. Here you can see the process, so the operation is going on, then the sample is taken out, it's sent to the histopathology lab, it's embedded, it's stained, it's analyzed, but this takes once in a while 8 to 10 days in order to get the result. The question is, or the unmet need is, we need somehow a rapid, reliable feedback mechanism on this tissue status, but already at that stage, we should do this either as a bulk when it's taken out or in vivo. And this means that if we do it ex vivo, we would like to look at the specimen itself, at the surface. We'd like to characterize by optical techniques the surface. Then certainly we need to analyze, interpret the data, and the idea behind this is, can we identify still tumor cells on top of the tissue because this will give the information that there is still tumor inside, because if it's still tumor on the surface, it's still inside the body. So the surgeon has to go back and take out more tissue. And if the surface is tumor-free, then certainly then the exploration can be stopped. And the other idea is, when this is being taken out, why not looking directly in vivo? So you guide the physician in order to tell him where's the tumor, how deep you have to go in order to do clean surgery. Well, this means new methods are needed in order to do this interpretation. And this means we need molecular sensitive imaging technologies for ex vivo, but also for the in vivo. And what we need at the very end is somehow a multimodal approach. This means the combination of different techniques. Because if you want to be fast, then the ordinary Raman spectroscopy will not work, because it's really not fast enough. If you want to measure something like, let's say, the colon tissue, this is the length of 6 meters. No way that you can do this somehow with Raman spectroscopy itself. So we need somehow a multimodal approach in order to be very fast. And what you can see here is more or less the situation. So here is somehow the tumor, but it's hard to see where the tumor ends. And this is why we want to use, for example, here our multimodal approaches. So this means we want to use, instead of just the white light image, we want to use, for example, an endoscope, which is based on multimodal imaging. And a multimodal image would look like this. So you have something like information on, for example, the lipid distribution, but also here on the different tissue types. But this will be very difficult to be interpreted by a physician. And here, for example, the deep learning AI plays an important role, because this is chemical information which can be easily translated into something what the physician can understand easily. And this is, for example, we can translate this in a HE stain. So here, for example, we have the diseased tissue, and here we have the healthy tissue. This is where the tumor border is, and this means in this area it has to cut. And this is somehow the idea we want to go. We want to translate our multimodal image in something that the physician can directly understand. Or the other way around is, very often the physician are just asking us, I'm not interested in any information, but the information should be healthy, diseased. This is red and green. This is the information they want to have. And this is what we are aiming for. And here, especially then, the deep learning, the machine learning is of utmost importance. And the idea behind this, a picture is worse than 1,000 words. And this is what brings me now towards the intraoperative cancer diagnostics, but you want also to go for therapy using light. And this is something which is also quite unique. And again, here, when we try to develop a therapeutic approach, then the deep learning is of utmost importance. And what we want to use is these nonlinear imaging technologies. What does it mean, nonlinear imaging? Well, this is something I would say is also quite simple, like Raman spectroscopy. The only difference is you need now not a CW laser, you need a pulse laser. The laser we are using have a pulse length of something like 20 to 60 picoseconds. They are coming from a fiber laser. And what can we do? If we take, for example, 2 wavelengths, then we can easily tune these 2 wavelengths to a specific Raman mode or vibrational mode. We can look at lipids, proteins, but we can also go for the DNA. So this means we will go for a single excitement of those modes. And what you can nicely do, if we have excited these modes, then they are coherently vibrating. And this coherent vibration can be easily probed by a third laser pulse, because this is like a, let's say, a break grating we are introducing inside the tissue. And then we get this scarce information out, the coherent undistocks, and the big advantage is that there is no fluorescence disturbing. And fluorescence is a big issue for Raman itself. But the big advantage is, since we're using pulsed lasers, we get a lot of information in addition, because you can easily go for two-photon excitation. And two-photon excitation, you can measure either the intensity or you can measure the lifetime. If you measure the intensity, then you can also go for elastine and NADPH, for the lifetime and intensity, giving you similar information. The intensity can be, let's say, changed because of bleaching, but the lifetime is not being affected. And the lifetime certainly gives you also the opportunity for metabolic imaging. So you can also go for more discrete information. And what is also quite important, we can also go for second harmonic generation. So this means not fluorescence, but we get second harmonic generated signals, but just from molecules which have no centrosymmetry, like collagen or tubulin, and this means you get structural information. So this means you are using one laser or two laser wavelengths, you put this in your microscope or your endoscope, and you get all this information at the same time. And the beauty of this approach is a fiber laser is quite small, and at the very end, these are distinct wavelengths. You don't need even a spectrometer. You just need filters in the fast detector. At the very end, we can miniaturize this device quite strongly. So what does it mean? So if you look, for example, here on human colon thin tissue section. So this would be, for example, a KUST image at 2,815 per centimeters. Here we have the fluorescence, the SHG structural information. We can nicely overlay this. And if we then zoom in, then you can see here, for example, we have some blood vessels, here some adipocyte tissue. And what we get is more or less label-free structural and chemical insights. It's non-invasive, and we can do optical sectioning. What does it mean? Optical sectioning means you can even go for depth resolution. You can go, depending on the wavelengths we are using, up to 200 or 300 microns. If we use wavelengths at 1800 nanometers for the excitation, we can go even millimeters into the tissue. And this optical sectioning means, because the signal, these signals are just produced within the laser focus, because these are non-linear processes, then you have also direct confocal information. So you get this information just out of a 1 micron thick layer. This means you can really go deep into the tissue, and you don't have information from the upper or the lower layers. And this makes it quite unique. And going back in time, so this was in 2013 and 13 and 16 where we published this paper. These are the first paper we have done, multimodal imaging, and the color code is here. The two-photon fluorescence in green, SHG is in blue, the cars, the lipids, the adipocytes are in red. And if you are a little bit aware, then you can see this is where the tumor is. In this case, also here, where the green is where the tumor is. And here we have colon tissue. This is where the healthy tissue is, and here where the diseased tissue is. Again, you need to know a lot of information, or you need to have a lot of information in order to understand these images. Therefore, this was the idea. We need to interpret this in something, or translate this in something the physician can easily understand. And now we come to somehow the automatic staining, and the idea behind this, we take this multimodal image, as I mentioned this at the very beginning, at the motivation, and we won't not require any staining because we have this multimodal image. Then we want to use, let's say, we want to use this mathematical approach. And this leads to the way that we also need no image registration at the very end anymore. And we would have a real-time assessment of the disease. And it's not just that we can produce an HE stain, we will be able to produce many different stains. Because in histopathology, different stains are being used. And the chemical information should be able to translate this in all the different stains. And here, for example, we are using this so-called generative adversarial networks. How does it work? So we have a source image and we have a target image. So the source image is our multimodal image. The target image is the real HE stain. And then what you build up is a generator, and you have this convolutional networks, and you are scaling this down to the generator you are trying to produce of the source image an HE stain. Out of the target image, with the generated image, then you build a discriminator, and the very end, the idea is that the discriminator is telling you this is true or this is false. You can do this even in a cycle gun approach, where you have two generators and two discriminators, and I can show you in a second that this is even more reliable. So how does it looks like? What we see here, this is again colon tissue, but not cancer tissue. Here we look at bowel disease. And the bowel disease is an inflammatory disease of the colon. And here you can see that there is almost no crimp structure anymore present. This is the target image, and here you can see these are still some crypt structures there, but normally they should be completely filled with nice crypts. And these are the generated image. You can see we can nicely produce out of this based on this target image by the generator and the discriminator. We can then tell you what the difference is, the true or false. And here with the cycle gun, you can see here a certain tile structure, but if we zoom in, then you can nicely see that here we have much more precise information. The tile structure will be gone if you are using much larger set of data. And this is somehow also the problem always. You need to have large data. Here you can see from the HE stain, this is where the crypt structure is, and this is nicely preserved here. But this is more or less the original image, which has been translated here into the HE stain. And as I mentioned before, so what is our aim? We want to produce those data on the surface, for example, on a tumor, and then overlay this information directly on the tumor, and then the physician should be able to see is the entire tumor being taken out or not. Here, just another image, and here you can see, I should put it in a different order. Here you see this is healthy colon tissue. Here you can nicely see the crypt structure, and again, this is the cycle gun has this tile structure, but this will be gone. You can go to a larger set of data, but it's more precise compared to the gun itself. Well, let me go to a case study. Case study in terms of, does it work? Can we really look at large specimen with this multimodal approach on a real specimen? What I have shown before was just slides, tissue slides. And the idea is not to work on a tumor, because you can't do just some, let's say, preliminary experiments on a real tumor, because this will hurt the patient. In the case you are destroying the tissue, then there's nothing going to the histopathology. But what we can easily access are human lymph nodes. And here you can see a human lymph node. This is 1.5 centimeters. This is already a quite nice size. Would be also challenging, because what you have seen before is much smaller. Can we really measure this with a nice resolution of subcellular resolution? So the idea behind this was we want to explore the toolbox. What type of modalities can we use, and can we also relate these modalities at the very end to the 3D structure? Yeah, the first topic was this 3D structure we want to get by a 3D reconstruction using photogrammetry. And then the LSM information we want to use, for example, then cars to photofluorescence, and not SFG, but SHG, because this laser we have been using here was better for some frequency generation, but giving you the same information like SHG, we will get more signal. Well, what does the idea looks like? So this is the lymph node. It's sticked on a needle. Now we take first the 3D information, and this is now the real 3D reconstructed information of the lymph node. So this is 1.5 centimeters. And at the very end, what we want to do is we want to measure, and now this is now being let's say the artistic part. So this is still the real 3D reconstruction of the lymph node, but now this is the artistic art, because at the moment we have not been measured this way. This might be the future, but nowadays I will show you how we measure this. And then we'd like to overlay this information directly on the tumor, the multimodal image, and afterwards also the generated HE image. Yeah. So why didn't we have measured this in this way? Certainly because it's way too challenging, because it will be in air, it will be drying, we will produce a lot of drying artifacts, and it's very hard because it's a 3D structure to really be always something like 20 microns beyond the surface. And therefore, the approach was different. We put this in this tile. We put it into a buffer solution so that we have no drying artifacts. And this way we can have a flat surface and we can measure something like 20 microns beyond the surface, because we don't want to measure it in any liquid or let's say the surface coverage. And so we're using different filters. So we used SFG. We measured here, you can see also SHG, 2 fluorescence areas or 3 fluorescence areas, and CARS. And I'd like to show you what are the findings. And keep in mind, this is 1.5 centimeters. This is the tumor, this is the lymph node. And here you can see the distribution of collagen. This is FHG. Here we have this connective tissue, some fluorescence and NADH FAD. Here you see some fluorescence of lipophytic fluorophores and the connecting to the adipocytes. And here you can see the adipocytes. What is quite nice, we do this with subcellular information, so we can easily zoom in and we can overlay all this information. And here you can see the adipocytes, you can see the collagen structure, and you can nicely see where the enzymes are located. Now the question is, can we also generate out of this an HE stain? So this is the entire lymph node surface, and this is now being zoomed in. And here we can also do this with an HE stain, so we can translate this also in HE stain. We can also zoom in, and you can see that we have similar information here on both slides. The big advantage is that this information can be easily interpreted by the physician, whereas this information is still hardly understood. You need to know what you are looking at. Now, the challenging part is to get this back on the 3D structure, and what I showed you before was the 3D reconstruction, so we can already put this back, but it's a lot of mathematics behind this in order to get this flat information being back on the surface. This took us months in order to explore how we can do this. But as I said, we want to go further. So this is somehow a proof of concept, but we will now go also for robotic system in order to do this ex vivo. But the other approaches we want also to go for in vivo. So these are 2 parts we are still looking at in very details. Now I'd like to show you some ideas and first results for in vivo endomicroscopy. And this is the probe we have developed within a German research project. And this is what the probe looks like, a rendering. So this is, again, something which is nice in Jena, because, as I said in the very beginning, we call it the Optics Valley. We have many companies working in optics and photonics. For example, here the company Grintech was designing together with us this entire endoscope. And what does the endoscopes look like? So we have a field of view of 650 micron, and we have 1 micron lateral resolution. So we are subcellular, we get subcellular information. For the light delivery, we are using this fiber laser at 795 from TAM and 1030 nanometers for the Stokes. So this is 1 fiber laser, and we have a second fiber laser, which we use for the ablation. And I said this is for the therapy part. I will come back to this in a second. For the light delivery, we use a hollow core fiber, which is being produced at the IPHD in order to have minimal dispersion, because we are using pulsed lasers and we have to overlay them, and they have different energies, different frequencies. And then this is what the scanning looks like. It's just a galvo scanner system with some collection optics. Then we have the collection fibers and one for the nonlinear imaging. This is for light delivery. And this is something special, but the physicians ask us if we can also add a channel where we can use, for example, ICG, this indocyan green. This is a fluorescent dye, and this is a dye which is allowed to be used in humans. And what happens if you use this dye, for example, if there is somewhere a tumor, there is more growing, more growth, more proliferation. And this means that this fluorescence is being increased, and therefore they want to have also this channel. Since we are just working with ex vivo samples, this is not being used at the moment. And for the detection, we are using just filters and 4 PMTs for these 4 channels. So this is what everything looks like. You can think it's still bulky, but this is the probe head, and this we will use, for example, in humans, then with the robotic system. This is the scan stage. This is just the open room. Here is the laser. This is the electronics. You can see there is not too much really, or it can be even miniaturized further. And we did first experiments on isolated samples, slides from patient. These are already very quite large. So we had included in this little study 30 patients, 20 samples. We'd first taken full sample overview, and then afterwards everything has been stained. And then with the pathologist being interpreted, he's doing the annotation. Then we do our data pre-processing, machine learning in order to interpret the data. So the first thing what we have to do with our data is we have to remove the illumination artifacts, because we cannot measure the entire area at once. Because we are using a galvo scanner at the edges, there will be a little bit less intensity than in the middle, in the center. This means that you have always these tile effects, and this you have to remove. So this is uneven illumination correction, the first thing. Then the staining is being done, the annotation mask, and then we have a registered image. And what did we do for the deep learning this time? So here we used a semantic segmentation approach. So this is here our specimen. Then we used something like a chessboard and a U-Net 3+ for training and for testing. And what you can see, we used the same sample for training as well as from testing. And the first thing was we went for 6-class segmentation, and here you can see for the testing, then for the average specificity and average sensitivity, the specificity was quite nice, 98%, the sensitivity 78%, and 6 classes means we went for healthy tissue, tumor stroma, other tissue necrosis, tumor, and background. But the physician also asked us, why we are going for so many classes. I'm just interested in healthy and diseased tissue. So this means we have a binary segmentation also done. The specificities went down a little bit, but we have a nice improvement of the sensitivity. But you have to keep in mind, this is a really small set of data, but already very promising results. And here you can see the ground truth. Here you can see the prediction. And this is already, I think, very promising in order to be pushed further. And the last thing I'd like to share with you is, can we really go also for something like what we call C-entry? Why not removing the tumor directly? Why do we need a scalpel in order to remove the tumor? Because light can do it in the same way, even in a better way, in a very controlled way. And so this means that we are using the CPA fiber laser, and 1032 nanometers for ablation. And the nice thing is we can use this in the same setup, the same optics. It's optimized for all these different wavelengths. And here you can see just the first proof of concept, which we have published already in 2019. And What you can really learn from this, we have subcellular precision, low collateral damage around, and it's very fast. Yeah, we can scan fast over the surface. And but this is nothing new, because this is used by many companies, for example, for the eye surgery, femtosecond, for dentistry, vocal folds, or neurosurgery. But we want to use it for now for selective tissue removal after diagnosis. Well, we have not been working on human samples, but we just used some chicken's meat slices. The sample power was something like 50 milliwatt. The energy is certainly a little bit higher than it was before, and the scanning speed is something like 60 millimeters per second. Here you can see we cut a hole inside. There you can see the transition region. And here you can see the morphological map now in 3D. So it means we can nicely cut out tissue or remove tissue, not cutting out, removing tissue. And here you can see the depth profile. Well, now the question is, we want to selectively remove tissue, not just remove everything, but because we want to be as precise as possible. And so this means that we first take an image, the first frame, and here what we can see is, for example, in red, this is adipocytes. And we said, okay, we want to remove this fat. So what does it mean? We have to translate this into something like an unsupervised approach. This is not really deep learning, this is just statistics. It's an unsupervised approach, a key mean clustering. We went for 4 clusters, and we said, okay, we want to get the region 3, the red cluster we want to remove, which is related to the adipocytes. Well, we produce out of this then a mask for the ablation, and then we use our system in order to apply it. So this is before, this is after. And I'd like to show you now, not in real time, but this is not being faster than it was done before. So we start our measurement. Here you can see the CARS measurements. You see the 2-photon fluorescence measurement. Here the SHG, the overlay. And what you don't see is the femtosecond laser ablation. But the femtosecond laser is also in parallel there. Now, so the first mask is being, so we produce first the mask. When the mask is being produced, we can do this in a complete automatic way.
Sure.
Just going back. So just 1 second. Oh, sorry, I was too fast. No, once again, I have to start this. So here you can see that when we start the measurement, then this image is being taken, and this is real time. So we can measure really this fast, and this is 1 frame. So these are 650 microns in diameter, and you can see you can directly remove also the tissue. This is before, and if you now look, this is afterwards. We can selectively remove it. This is somehow, again, a proof of concept in order to show that this might be something for the future. Well, with this, I'd like to summarize. I hope I could show you that really biophotonics and AI is something really going to personal diagnostic and therapy. And this is not certainly, these are results from our side, but when you look at the literature, then you can see there's really a big rise in AI-driven biophotonics for clinical application. And many have demonstrated their potential. As I hope I could show you that there is a potential in our technology as well in numerous studies. The major challenge is how to integrate this into the clinical workflow, and meaning to integrate this into the clinical workflow means also to have a medical product according to the medical device regulation, and also to prove that what you are doing is at least as good as what is existing, or even better, and it should be not more expensive. So our research focus is on merging linear and nonlinear Raman techniques together with other optical methods, but also advanced AI tools. The last topic I showed to you, we want to go for real-time interoperative histopathological diagnosis of tumor, but also tumor removal, and also for swift and accurate diagnosis and treatment of infection diseases. And as I mentioned before, we develop different devices which can be used directly then in the clinical setting or can be used in doctor's office, hopefully, in the future. Well, and I hope they could convince you there's a big potential for new methods because they are much faster, more precise, and at the very end, I hope that we can also convince that the costs are way lower than what is existing at the moment. Well, this is my group, so this is not the institute itself, so this is my department in the Institute of Physical Chemistry, together with my people from the Institute of Photonic Technology. Then funding is certainly needed and very much appreciated by the various funding agencies. And what's also quite important, having good collaborators. Yeah, we have many collaborators in different hospitals, in Jena, in Erlangen, but also in Copenhagen, and then many collaborators in the technical field. And I think this is also quite important in order to get the different competences together. And last but not least, I'd like to thank you with the thanks to Jena, the city of Light. Thank you.
Yeah, so any questions from the audience? Yeah, okay, there.
Thanks for your nice talk. I have a question about the spectrum. When we treat the spectrum to the AI for the machine learning or deep learning, do we need to define the weight of the spectrum based on the chemical information? For example, which part is more important, which part is less important? Because, for example, when we use Raman spectrum to detect the different cells for diagnosis, when the focus on the membrane of the cells or inside of the cells, the spectrum is much different. Maybe the difference is larger than the health versus disease group. So how can we solve this problem?
So at the moment, we are not really, so what we normally take is the fingerprint region, but we don't cut out any areas. And we are not doing any weighting. So when we look at, so we have to differentiate the topics. So if we go for the infection diseases, and even there are two different topics we have to address. If you go for the identification of the pathogens, for example, saying this is E. coli, this is Staph aureus or something else. What we have to build up is a database, and this is somehow a supervised approach. So this means that we learn let's say, the classifier, this is what E. coli looks like, and this is what, for example, Staph aureus looks like. And then the machine learning approach is more or less to identify the most important criteria which are different between the two species. And this has been to, let's say, put in such a way that you can put this also for the other species. So there is no weighting of the spectral information because we really don't know. But I will come back to the weighting in a second. When we look at the antibiotic resistance measurement, then there is no weighting needed because what we do is we have the bacterium and we have the antibiotic and we look at the biochemical interaction and are there any changes in the molecular composition? So therefore, we don't need to look at the weighting. We see there are some spectral changes, and we don't. So it would be nice if we understand the changes, and we are looking also forward. But for the interpretation, if or let's say for the finding, is this an active substance or not? The interpretation is not needed. But certainly from the scientific point of view, we want to understand what we are looking at. And but for the machine learning approach, this is not really needed in order to get to this medical approach. What I have not shown is we're using also normal Raman spectroscopy for example, bladder cancer or head and neck cancer diagnostics. And there we also take the spectra as not as they are, but we do not any weighting. What we are very much interested in, and this is somehow something we are pushing forward at the moment, is we want to correlate the Raman data, for example, with metabolome data. And we want to correlate this also with lipodome data. And this means then that we can understand what is contributing to what decision. Yeah? But just using the Raman data itself is not sufficient. So you need independent data, and this is what we are trying to get out of this. It's somehow spatial resolved Raman and metabolome data, as well as then in the future also temporal. So if you have changes going on, but this is ongoing. But for this medical approach, where you really like just to identify what is going on, is this A or B, or is this sensitive or not? Is this cancer or not? This is not really needed. But our aim is in the future to have a little bit more understanding, not on the differentiation, but for example, to learn why is a drug active, cancer drug active, and what? Can we relate this to, for example, some spectroscopic data? This is the idea behind it.
Thank you.
Any other questions? Yeah.
Professor, to begin again, geo traps.
Well, it's better to have it. We have a recording. So,
Professor, thanks for the impressive presentation. I noticed you mentioned the image generated by your machine is hard to integrate. So you use an AI model to auto-staining the multimodal data to HE data. You also mentioned you would like to auto-staining it to other modalities, for example, HC or other things. So my question is like that: how can we let the doctor or pathologist trust our auto-stain image as real? So since I also read some papers about the water staining, the overall structure is very similar to the real HE image. But if we zoom in, we can see the detail of the seal actually is different. So how can we let the doctor trust our water stain image? I think it's a big problem.
Yeah. So I agree, but you have to be careful at what publication you are looking at. Yeah. So if you are just using the CARS or the SRS image, and you produce out of the SRS image by changing the color coding something what looks like the HE stain, you will always find differences. The approach here is different because we are trying to really translate what is present in the real AE stain to what is present in the multimodal image. Yeah, so these are different approaches. So if you just change the color code, then this is not a surprise that there is difference, because the nuclei normally are not really present. Yeah, and therefore I think the approach is different. But in order to answer your question more precisely, how can we, let's say, convince the physicians that what we are doing is reasonable? So at the very end, you need to be at least as good as the ground truth, which is the pathology. And if you find something new, and this we already did, for example, we correlate Raman data and multi-data with an HE stain, and our finding was that there are areas where still tumor is, where no annotation was. And when the physician went back, or the pathologist went back, he said, okay, this he has overseen. And I think this way we can really convince that these technology we are using are really of, let's say, help, because they are faster. And it's not replacing the pathologist, because at the very end we will give him just a new method in order to look at his staining methods. And when I talk about other staining methods, certainly the ground truth will be, for example, then a staining for the progression tumor marker, or this will be a collagen stain, or something else. Yeah. So first of all, we have to use these different stains, and this is also a big project which is run by Thomas Bocklitz's group. He has an ERC grant on this, where you want to correlate these multimodal images with 4 or 5 different stains at the same time. Yeah. But I think this is just the step by step. We have to convince the physician that what we are doing is as good as what has been the gold standard so far.
Any other question? Look.
Thanks for a very inspiring talk. So I have maybe 2 small questions. So the first is, I was wondering how subtle the Raman spectrum will change. For example, for different conformations, different structures, and if that change, essentially, I'm assuming you're probing the peak frequency, intensity, and maybe peak width. If that change is subtle, would that be a problem if you have low resolution of Raman spectroscopy? If the change is small, will that be an issue?
So it depends what you're looking at. So if I'm really very much interested in protein folding, yeah, then certainly I need different resolution, because then we have to look at very precisely what is going on, for example, in a protein structure. Because Raman is very sensitive to structural changes. So within a Raman spectrum, you can easily identify the different structural forms of a protein. So if I have an alpha helix, a beta fiber, or a random coil, if let's say the resolution of the resolution is way too large, then certainly those information will be gone. At the moment, we figured out that the spectral resolution we are using, this is around 10 to 20 inverse centimeters, is still sufficient in order to, if there is something going on in the tissue, and there you have to keep in mind, inside the tissue, and this is different if I have a real protein solution, the protein information is still present, but much broader, because it's overlaid by many others information. So the overall changes will be still similar, but I completely agree. If I want to go for protein folding, for example, in a liquid environment, then I need a complete different approach. And if I'm going for the UV, for example, then there I have really the resonance Raman and very distinct features which are quite narrow. And then I need a different resolution, otherwise I will lose information. It depends always on the question I like to answer.
I see. Thanks. Another question I have is, you mentioned you're making essentially a database for these different structures or molecules. Are you making that database publicly available so that others can maybe?
So at the moment it is difficult, yeah, because it's not that we don't like to do it, but the idea is we need to, let's say, publish data which are of value. And of value means that you have to consider all this entire FAIR principle. Yes. And the FAIR principle means not just that they are findable and they are interpretable, but if you want to make them interpretable, then you need to have the metadata. Yeah? Very precisely, and this is more or less the process what we are now looking forward, and also try to get some let's say connection to other groups working in this field in order to have this done in a comprehensive and let's say in a way that it can be really used in the future. And this, let's say, producing the data is one, but bringing them to the public is something completely else. Certainly we can publish everything, but the question is, can they be reused? And then we have to also define standards. And this is a challenging part of Raman, especially producing the standards. But honestly speaking, so these are the requirements from the German Science Foundation, that if you publish data, or paper, then you need to publish also the data in the future. Certainly, many journals already require this, but the European Union is going even a step further. They require even unpublished data, which has been produced by funding from the European Commission, needs to be published. And now we have also to figure out how to do this. Who will store the data? How will be the access of the data? Yeah. So there are a lot of questions which has been not answered.
Hi, Professor. Thanks for your presentation. And I have a little question that you used the nonlinear multi-imaging mode for cancer diagnosis. But the nonlinear imaging need to always focus in focus to get the signals. Would that be more easy if you use like luminescence from ICG to get the signals from the disease parts? Yeah.
So this is somehow for in vivo imaging, this will be somehow the idea to see where is the luminescence, and then you can restrict yourself directly to the area where you have more growth. And if this is related also to the morphology of the tumor, then you can localize the tumor much better. Yeah. But this is, therefore, we have reduced or we have developed this probe in such a way that we can use the ICG fluorescence as well as multimodal imaging at the same time. Yeah, so this is the underlying idea, and this was the wish of our physician, that might help to localize and to identify where the tumor is. And then with the nonlinear modalities, certainly we can more precisely identify where the tumor border is. Because to identify where the tumor is, the physician does not need any of our technologies. But for example, for head and neck cancer, to see where is the end of the tumor, yeah, there we need different techniques. And the same is for the brain tumor. For example, there now it's not ICG being used, they use 5-ALA. So 5-ALA is more or less one of these building blocks of heme. And if the heme is formed out of 5-ALA within the cell, this heme is highly fluorescent. If the iron is inside, then we have hemoglobin, then it's not anymore fluorescence. But the heme itself is very fluorescent, so this is being also used in order to see where is more growth inside the tissue. And this is, for example, something which is allowed now also for brain surgery or for bladder cancer surgery. And again, this might be the way to see where is the tumor localized, and then use the optical methods in order to see where the tumor border. And especially in the brain, it's of utmost importance to be very precise in order to not cut out function.
Okay, thank you.
Welcome.
Yeah. Okay. So because of the time limits, you're welcome to approach Professor POPP later. So let's thank Professor POPP again.
Thank you.